On the afternoon of the 10th of August, 1628, a crowd gathered along the waterfront in Stockholm because the most powerful warship in the Baltic was about to leave harbor for the very first time. Her name was Vasa. She had been 3 years in the building. She carried 64 guns on 2 full gun decks, and hundreds of carved and gilded figures covered her stern, because a warship in this century was a statement about a country at least as much as it was a weapon. The weather was almost nothing at all. A councillor writing to the king a few days afterwards described calm weather with a wind from the southwest and gusts arriving every now and then, which is exactly the sort of afternoon you would choose for a maiden voyage. She was warped along the shore, fired a salute, and set 4 of her 10 sails. A first gust laid her over, and she came back upright, so nobody was alarmed. Then, as she reached a gap in the bluffs at Tegelviken, a stronger gust pushed her further, and this time the water came level with her open lower gun ports. She did not come back. Water poured in faster than anyone could close anything, so she filled, rolled on her side, and settled on the bottom in 32 meters of water, roughly 1,300 meters from where she had started, in plain sight of the yard that had built her. Somewhere between 30 and 50 people drowned. Later in this video, we will look at why that is a range rather than a single number, because the reason for it is part of the story. And yet nothing went wrong that afternoon. The wind was light, the crew were sober, and every gun was lashed, which is why the inquest held 4 weeks later could not find a single person to blame. Whatever sank this ship had already happened, and it was a quantity that nobody in Europe yet knew how to calculate. 4 weeks after the sinking, 17 councillors and naval officers sat down in the royal palace and put the survivors under oath, so we do not have to guess what happened. The transcript still exists, and most of the obvious explanations die in it. The first is weather. Everyone who was on deck agreed that the wind was trivial. One officer said he would never have thought that any ship could capsize in such light weather, and the councillor's letter to the king calls it calm with occasional gusts. The second is drink. The prosecutor accused the boatswain of having been drunk, which would have been convenient for everybody, and the boatswain answered that he had taken communion that morning. Nobody pressed the point because there was no evidence for it. The third is loose cannon rolling to one side. 2 separate officers testified that every gun was secured, and the only exception was one small piece with no carriage, which was far too light to matter for a ship of this size. The fourth is ballast, and this is the one that is usually repeated today. But the ballast master swore he had gone below with a lantern and stowed as much stone as would physically fit, and the boatswain said the same thing independently. The hold was full. So the inquest arrived somewhere genuinely interesting. The master shipwright was asked why he had built the ship so narrow that it had no belly and could not right itself, and several captains said the hold was simply too small to take the ballast the ship needed. They had the right answer in words. What they did not have was a number. Nobody could say how much belly is enough or how much ballast the ship needed, because the quantity that answers those questions had not been invented. So that is where we go next. What actually brings a ship back upright? And how would you count it? Only 2 forces matter, and they pull in opposite directions. The first is the weight of everything the ship is made of and everything she is carrying. And although that weight is spread all over her, it adds up to a single downward force acting through one point, which naval architects call the center of gravity. The second is buoyancy. Archimedes tells us the upward push equals the weight of the water the hull has pushed out of the way, and that push acts through the middle of the displaced water, so it has its own point called the center of buoyancy. Sitting upright, those 2 points are one directly above the other on the center line. 2 equal and opposite forces sharing a single line of action cannot turn anything, which is why a ship at rest simply sits there. Now heel her over. The center of gravity does not move because it is bolted to the ship and the ship is rigid. But the shape underwater has changed. A wedge of hull has gone in on the low side and an equal wedge has come out on the high side. So the middle of the displaced water slides towards the low side. The 2 forces are now on 2 different vertical lines. 2 equal and opposite forces on parallel lines make what mechanics calls a couple, and the turning effect of a couple is simply the force multiplied by the distance between the lines. That distance is the whole of ship stability. When buoyancy has moved to the low side of gravity, the couple turns her back upright, and the further it has moved, the harder she is pushed back. Naval architects call that distance the riding arm. But watch what happens if the center of gravity is high. The same heel, the same wedges, the same movement of buoyancy, and now gravity is on the outside instead. The couple has reversed, so every degree she leans makes her lean further, and there is nothing to stop it. Here is the trick that turns all of that into arithmetic. Heel the ship a little and draw the upward line through the new center of buoyancy. Heel her a little more and draw it again. For small angles, those lines all cross at one point, sitting high up above the hull, and that point is called the metacentre. The metacentre matters because it converts a question about moving shapes into a question about the order of two fixed heights. If the metacentre is above the center of gravity, the ship rights herself, and if it is below, she does not. The gap between them has a name, and it is the single most important number on any ship. It is called the metacentric height. So we need to know how far the metacentre sits above the center of buoyancy. There's a beautiful answer. Take the shape the ship cuts out of the surface of the water, work out its second moment of area about the centerline, and divide by the volume of water she displaces. The second moment is where the sensitivity hides. Every strip of that water plane contributes in proportion to the cube of how far out it reaches, so widening a hull is worth enormously more than lengthening it. It also means that anything which narrows the waterline as she leans takes away stability faster than you would guess. Now, we could simply assert that formula, but this channel does not do that. So the model computes the same distance a second way that shares no algebra with the first. Heel the hull by 1 degree, find the center of the wetted volume by direct integration, and measure how far sideways it actually went. The center of buoyancy moves 42.5 millimeters. Divide that by the sine of 1 degree, and you get 2.436 meters. The formula gives 2.436 meters. The two routes agree to better than 1 part in 1,000, and they agree again at 2 degrees and at 4. Add that to the height of the center of buoyancy above the keel, and the metacentre of this hull sits 5.04 meters above the bottom of her keel. That number depends only on the shape of the hull and how deep she floats. So it was knowable in 1628 by anyone who could measure a ship. Nobody knew it was worth knowing until 1746. The metacentric height is only the beginning because it describes the ship at 0 degrees of heel, and no ship ever capsizes at 0 degrees. What we actually want is the riding arm at every angle, which means measuring that gap all the way over. So heel her 1 degree at a time and plot it. The curve leaves the origin as a straight line whose slope is exactly the metacentric height, which is why that single number is worth having. Then it bends because once the deck edge starts approaching the water, the buoyancy center stops moving in a straight line. And for a hull like this one, sealed all the way up to the weather deck, the curve keeps climbing to somewhere around 80 degrees before it turns over. On paper, that is a wonderful ship because it means you could lay her almost flat and she would still be trying to come back. But that whole calculation assumes she is a closed box, and this is where a warship of this period stops being one. There are gun ports cut through her side. They sit little more than a meter above the water, and on a voyage in home waters they are open. So the curve is only true out to the angle where the first hole goes under. Past that, water is coming in, the weight is changing, and the shape is changing, and the arithmetic describes a ship that no longer exists. That is why the modern rule asks for the area out to 40 degrees or the flooding angle, whichever comes first. Because area is what really matters. A gust does not apply a polite steady lean, it delivers a shove, and a shove carries energy. The energy the ship can absorb is the area underneath the usable part of this curve, and if the usable part is a sliver near the origin, then so is the energy. One more feature makes this worse, and Vasa has it badly. Her sides lean inward as they rise, which shipwrights call tumble home. It looks elegant and it keeps weight low, but it means the shape she cuts out of the water surface gets narrower as she leans. And since the water plane counts every strip as the cube of its distance out, she loses riding ability exactly when she needs it. That is the tool finished. So let us build her. Length between perpendiculars, 47.5 meters. Beam, 11.7 meters. At the inquest, her lieutenant gave her draft as 14 feet forward and 16 feet aft, which averages to about 4.5 meters, and museum publishes her departure weight as 1,200 to 1,250 tons. There's exactly one thing in the model that is not measured, which is how quickly the hull narrows towards the bow and the stern. We set that so the model weighs what the museum says she weighed, and then we check the shape it produced. Her block coefficient comes out at 0.49, which is where a fine warship of that century belongs, so the hull is not a fantasy. Now, run the calculation. The center of buoyancy sits 2.6 meters above the keel. The metacentre sits another 2.44 above that, and so the metacentre of this ship is 5.04 meters above the bottom of her keel. That is her ceiling. Her center of gravity has to come in underneath it. Adding up what we know she was carrying, the hull itself is 600 tons, and most of it is high, because the upper works were tall and heavily built. 120 tons of stone ballast sits right on the bottom. 60 tons of bronze guns sit on 2 decks well above the water, and the masts and rigging put another 50 tons an average of 18 meters up. That schedule puts her center of gravity at 5.15 meters, which is above her metacentre, so the calculation says her metacentric height was negative. Now, a genuinely negative value means a ship cannot sit upright at all, and she plainly did sit upright, so our estimate is about 1/4 of a meter too harsh. That is honest, and it is well inside the uncertainty in where the hull's own weight sits. So take the kindest value that is still consistent with what witnesses saw and give her a metacentric height of 14 centimeters. The modern international minimum is 15. She is on the wrong side of a line drawn 3 centuries later, and that is her best case. And now the number that ends the argument. Her gun ports go under at 10 degrees of heel. Before she reaches 10 degrees, the largest riding arm she can produce is 2.6 centimeters, which is about 1 part in 440 of her beam. So the area under the usable part of her stability curve comes to 2.4% of what a ship is required to have today. The obvious repair is more ballast. Put more stone in the bottom, pull the center of gravity down, and buy back some metacentric height. So let us actually do it 100 tons at a time and watch both of the things that happen. The first thing is the good one. 100 tons of stone on the floor of the hold drops her center of gravity by about 30 centimeters, and her metacentric height goes from slightly negative to nearly 19 centimeters, which is finally on the right side of the modern line. The second thing is the price. Those 100 tons have to float, so she sinks deeper into the water. Her waterplane covers about 357 square meters, so every 100 tons pushes her down another 28 centimeters, and there are only 104 centimeters between the water and the bottom edge of an open gun port. Watch the 2 curves. Metacentric height climbs steadily as the stone goes in. The angle at which the gun ports go under falls just as steadily because the sills are getting closer to the water all the time. By 300 tons, she has a decent metacentric height, and her gun ports flood at 2 degrees of heel, which is worse than useless. And at 400 tons, the sills are under the water while she is sitting perfectly upright at her moorings. There is no amount of stone that produces a good ship, because the 2 requirements pass each other without ever both being satisfied. The men who loaded her had this exact argument out loud. The vice admiral told the ballast master he was loading too much stone, because the gun ports would come too close to the water. The gunner asked how he was supposed to ballast her more when the ports lay only 3.5 feet from the surface. Every one of them was right, and that is the tragedy. The trade-off was understood perfectly well in words by the people standing on the deck. What nobody could do was put a number on either side of it and see that the 2 numbers did not meet. The answer was not more ballast. The answer was a wider hull and a deeper hold, and that decision had been taken and closed 3 years earlier. About a month before any of that, while she was still tied up beside the castle with her ballast already in, the captain went to Vice Admiral Klaus Fleming and told him plainly that the ship was crank, which was the seaman's word for a vessel that leans too easily. Fleming came down to watch a demonstration. 30 men ran from one side of the upper deck to the other and kept running so that she would start a roll. The master's testimony records what happened next in one sentence. The first time she heeled 1 plank, the second time 2 planks, the third time 3 planks, and the admiral told them to stop because if they had gone on, she would have capsized. Now, that demonstration has a modern name. It is called an inclining experiment, and it is still, today, exactly how the metacentric height of a finished ship is measured. You shift a known weight, a known distance across the deck. You measure how far she leans, and the metacentric height falls straight out of the arithmetic. So put their numbers into it. 30 men, call it 68 kilograms each, moving 4.6 meters out from the centerline. That is a healing moment of about 92 kilonewton meters applied to a ship weighing 1,225 tons. A sound warship with a metacentric height of a meter and a bit would have answered that by leaning about 4/10 of 1 degree, which means you would not have been able to see it happen at all. Nobody would have written it down because there would have been nothing to write down. Vasa leaned about 3.15 degrees on each pass, and 3 passes takes her to roughly 9.5. Her gun ports go under at 10.1. Fleming stopped that test about 7/10 of a degree before the sea would have come in through her own gun deck. And he was right that one more crossing would have finished it. There's one more thing hiding in it. 3.15 degrees at her beam drops her side 32 centimeters into the water, and a strake of oak planking on a ship that size is about 1/3 of a meter. 1 plank, 2 planks, 3 planks is the same measurement as 3 degrees per pass, taken 4 centuries apart, and the two agree. So the number existed. It was taken in public, in front of the officer responsible, about a month before she sailed, and everybody watching understood what they had seen. What did not exist was the arithmetic that turns 3 planks into a quantity you can compare against a limit. Fleming said he wished the king were at home, and then let her sail. The treatise that defines the metacentre was published in 1746, and an equivalent test appeared independently 3 years later. That is 118 years after Vasa went down. Every single ingredient of the calculation, though, was already lying around in 1628. They could weigh things. They could measure a hull. Archimedes had been available for 18 centuries. Nobody was missing a fact. What was missing was the idea that you could combine those facts into one number and then compare that number against a limit. That is worth sitting with because it is the actual shape of most engineering disasters. The evidence is usually present and often alarming. What is absent is a quantity, agreed in advance, that turns alarming into unacceptable. 3 planks is a story. 14 centimeters against a required 15 is a decision. And notice what the modern rule chose to measure. It does not ask only for a metacentric height. It asks for area under the writing curve, out to 40 degrees, or to the angle where water can get in, whichever comes first. In other words, the rule is written in the language of how much the ship can absorb, not how stiff she feels at rest. Now the debt from the beginning of this video. The death toll is written as a range because the sources genuinely disagree. 3 people who were there wrote letters that week giving about 50, about 40, and about 30, and the council told the king that most had escaped but that they could not yet say how many had not. Skeletal remains recovered from the wreck give a floor, but some of the dead were pulled out and buried in 1628 and left nothing behind to find. So the gap between the bones and the deaths cannot be closed. And the honest answer is a range with a reason attached, rather than a number that looks tidier than the evidence. She was found again in 1956 and lifted in 1961 after 333 years on the bottom. 98% of the wood is the original oak, and the reason she survived is that Stockholm's water is barely salty, so the shipworm that eats every other wreck cannot live there. Which means you can go and stand in front of the answer. The tumble home is right there, the gun ports are right there, and they're about a meter above where her waterline used to be. She is the only ship of her century you can look at, and she is only available to be looked at because somebody got the arithmetic wrong.